Welcome to the fourth order bandpass filter, constructed from two second order Butterworth circuits, which are also filters in themselves. This is a subset of a larger project that I have worked on since my sophomore year within the pursuit of a degree in electrical engineering. To start off with, let us look at our breadboarded circuit. Here we have two op amps, one located in this top section here and one located in this bottom section right here. This top section one is responsible for limiting the cutoff frequency at 1 kHz, whereas the lower one is responsible for limiting the cutoff frequency at 10 kHz. These are our lower and upper limits, which determines the bandwidth that is actually passed, and all other bandwidth and frequencies therein are attenuated or reduced in magnitude of the input signal in which it is found within. The resistances and capacitor values found in this circuit were carefully calculated and then approximated using combinations of parallel and series connections to best meet the design requirements of this filter. Now, the next step was to connect a bunch of posts around the outside of the circuit in which to mount all the diagnostic tools. Let us discuss those. In the back here, we have our power. These two inputs supply our positive and negative supply rails to our op amps, both at 15 volts. The upper one is at positive 15 volts and the lower one is at negative 15 volts. I then set the ground in this area to be 0 volts, such that our entire circuit is able to have a range from positive 15 to negative 15 with its supply rails, which allows us to have a greater input amplitude for our circuit than if we had used simply a 0 to 15 positive rail. Also, during the construction of this circuit, due to the fact that we are building it on a breadboard and with all these wires and not soldering the circuit, there is a lot of noise that has been introduced into the circuit. Therefore, by increasing the amplitude of our input signal, we are able to avoid the noise artifacts as much in our diagnostic of our circuit. Also, there are limitations to the op amps that we used in this circuit. The 741 op amps that we used are limited by their skew rate, which is the maximum response that the signal can move in amplitude, and that affects the range in which the op amps can operate in, as in its frequency range. Later, I will show the actual artifacts on the oscilloscope so you can see what I'm talking about. Now, we are moving on to the other parts of this demonstration. First, we have our DC power supply set at 15 volts on channels 1 and 2. Now, I will have to walk over here for a second so this light doesn't turn off. Sorry. Okay, where we were at was, as you can see, I've connected this up so that we have our positive 15 on this channel 1, and we have 15 on channel 2. The secret here, or the way you're supposed to do it, as you see, I have connected this between the positive of channel 2 and the negative of channel 1, and then I have connected the negative of channel 2 to our negative supply rail, and that was the positive supply rail, which came from this side right here. And then from the middle tap, as you can see the middle tap that's connected between the top of channel 2 and the bottom, the negative of channel 1, that is then connected to our ground in our circuit. Now, what I would like to do for you is also show you that this is our multimeter, basically, that lets us check all our resistances, capacitance values, and everything, which is very important to use. I mention this because this tool is just as important as the oscilloscope and the power supply and everything else I'm showing you. And it's important to know how to use all these tools. This is the oscilloscope, and as you can see, I have my two waveforms on there. And down here, let me refresh this to get this thing to work. Just wiggle this a little bit to get it off its mode. It's a screensaver. You see I've got it set at 5 Hertz. What I'm going to be demonstrating is some information about the characteristics of our circuit. But once again, I'm going to walk over there because the light keeps shutting off, and I have to get this video recorded so it doesn't shut off on me right here. Okay. All right, we'll be back in a minute. Okay. Okay, so looking at this function generator, you see I've set it at 5 Hertz. I'm going to do a frequency sweep from 500 Hertz up to 20 kHz. This will allow us to see how the circuit, which is our fourth order bandpass filter, handles the frequencies. And I'll explain what you're seeing. Okay, so first of all, we have it at 500 hertz, and you can see that the frequency for channel 2, which is blue, and channel 1, which is yellow, corresponds to the blue being our input signal and the yellow being our output signal. I also, with my circuit, this is something important that everyone should do, is within my circuit I use blue for input and orange for output, red for the power supply rail coming in, black for the negative power supply rails for the op amps, and I also tried to use yellow for the voltage follower within the two op amps, and the other connections I used other wires to keep track of where it's at. This is very important. If you can use color-coded wires, it makes your life a lot easier, so I would recommend doing that. Also, make sure you have a good calculator that you know how to use. Yes, okay, so back to this. I'm going to go and make sure that light does not turn off again, and I will be back in 1 second. Then I'm going to go and do a quick frequency sweep and show you that information. All right. Okay, so here's what we're going to do. And while I was working on the circuit, there was a lot of things that I had to discover and troubleshoot and figure out why things didn't work. That is a very important skill to develop, is setbacks and not getting discouraged and being able to work through it and problem solve. Because when you get out in the world and you have to make a living, or you're just having fun with the circuits or whatnot, it's important to develop a sense of being able to troubleshoot things on your own so that you can get things done. Because if not, it can be very discouraging, but it's something that you have to go and do. It's sort of like a trial by fire. But anyway, I just thought that would be important to kind of let you know. Alright, so here we go. We got our function generator and our oscilloscope, and now I'm going to go and sweep through those frequency ranges that I told you about using this knob right here. Now I'll explain what you're seeing here. So as we move, you're going to notice that the frequency of our input and our output are going to remain the same. This is because this filter is not, this portion of my main project does not have any gain in it, gain element. It is a unity. It is in unity, so there is no gain. Anyway, so that's the reason why there's not going to be, what you're going to see is that there is going to be attenuation instead of gain, and that is how the frequencies are blocked or passed. It decreases the magnitude of the signal so that the signals that you do want to pass are stronger and you can see them. So you're going to be able to actively see that. And I'll explain some other things that you're also seeing. So as I increase the signal, and I've set this already up ahead of time so that you could see this. So that's why it's all ready to go. You have to normally adjust all this stuff over here to get the best view. Anyway, so let me keep going on. We're now at 700. And we're going to keep going up a little bit here. Now we're going to go to 8 and notice on the bottom there that how the frequencies change. notice that right now they're at 800. But also notice that the peak-to-peak values of our yellow output is going to increase as it reaches the middle of our pass band. And that is characteristic of what you're wanting to see. And you can see as it gets closer, we're at 1.1. So we're not really even barely in where we were wanting. But see how the signal is maintaining the same frequency, but the peak-to-peak value is slowly increasing. That's because it's attenuating the other signals. If we had multiple signals, then you would see the signals that you are looking at and wanting, I mean the ones you're wanting, you would see them increasing in magnitude, and your other signals, you would see the ones you didn't want to pass, you would see them being attenuated. I'm sorry I have to keep doing this with this camera, or not camera, but this sensor, but if I don't, then it turns black in here, and this is a long video, so I want to make sure it doesn't turn off on me anymore. So anyway, so I'm going to keep going and adjusting this up, and as you can see, it's at 7, and as I can keep increasing this, well, I mean, it was at 1.7, now it's 1.9 kilohertz. As you can see, it keeps on going up, and notice that the magnitude of our output in the yellow down there is increasing, but our frequency is maintaining the same frequency, like it's at 2 kilohertz now. Now we're continuing on, and now we're only at 2.2, 2.3, 2.4, and so on. Now there are some other things that you may be able to notice. I don't know. It took me a while to go and analyze all this stuff, but what I noticed, and I did a lot of reading and research on this stuff also, is that I realized that specifically when you're doing this stuff, you also need to research the op amps that you're working with. And what I learned about the 741 was that there's a slight phase shift when you are moving in your frequency. So as you get closer to the band pass that you're trying, the range, the band of frequency you're trying to pass, the phase of your input and output align up more. But then as you move away from that, there's a phase shift. And I am not sure yet, and I have to admit some things I don't know. I'm not sure if this is just with the 741, but it may be a characteristic of all op amps. I'm not certain on that, but I do know that with the 741 that is a characteristic of it. I also know that it does. The 741 has a slew rate limitation, which I will show you that in a second, where you can actually see that. Okay, so we're back. We're only at 2.7. So let me go on, because it's taking a little longer than I wanted to. But I wanted to make sure you really understood as much as I can. I'm not really good at taking these videos, but I guess I'm out of my comfort zone. But I will attempt to do this. And normally, if I'm just talking to someone, I can do it, but recording is a little bit more difficult. But it's a good habit to get into, I guess, learning from this. Okay, so now we're going to keep increasing this, and increasing this, increasing this. So right now we're at 3.3, 3.4, 3.6, 3.7. And as you see, it's going to keep doing the same pattern that I was telling you about. See how it's slowly becoming into phase? See how the output input and the input are slowly getting into phase? See how they're lining up like that? That's because that thing I just discussed about the phase difference. Now we're now at 6 kilohertz, and as you can see, the peak-to-peak amplitude has now increased. We're a little bit past mid-band right now of the frequency bandpass we're trying to pass, and we are, as you can see, it's lined up pretty well right now. If we drop back to 5, again, look at that, it's right in the middle. See how it's as you go closer, go to 6, see how it's getting closer and closer and closer. Anyway, so also you have to take into account that the divisions are different on here. So what I said earlier about the phase shift taking place, this was something I read about in the in an article I read, but I also understand that if you look at the divisions down there, this is 2 volts versus 10 down here, but there is also something that I read, that there is a phase lag lead depending on with this particular op amp. So I wanted to show you that, but it's probably just because I have the different the 10 and 2 down there, which shows our divisions. They're different, and so that may be, and I'm pretty sure is what you're actually looking at, is that instead of that other, the actual phase discrepancy due to the op amp. I wanted to show you that, but it may not, it's probably not what you're actually seeing there. So it's probably just the difference in divisions, and is just moving along as to just give a picture of kind of the general form of it, of the wave, the sinusoidal wave. Okay, so going on, I wanted to show you this one other thing that I thought was pretty cool. If you look on here, as you keep going up, and we're at 6.4, 6.5, 6.6, now we're going to move all the way up. We're going to keep moving, and we're going to move all the way up to R10. Now, you see that? Okay, do you see that little spike on the output yellow there? That right there is caused by the skew rate, the limitation of the skew rate on with our op amps, which are the 741s. So as you increase and you keep getting up closer to 10, and now we're at 10, you see how it's increasing slowly? That's because this op amp skew rate has limitations starting around 10 kilohertz, and if we go past this, you're going to see that increase rapidly. Also, you're going to see a decrease in the peak-to-peak gain. As you can see, it's going to start dropping here. See how it's starting to drop as we keep going past 10. And see how it's going down. So we know it's working, even though we have this skew rate limitation. I was still able to utilize this op amp to do what I needed to do, or for demonstrating this. But if you really wanted to build this circuit in real life, then which this is real life too, but I would have selected a different op amp that didn't have these limitations, because it does mess up some of the demonstration here, because I can't, as you can see, that it's at 2.84, and we're at 14. Now we're at 15, and see how it's starting. It's dropping now to 256 volt, 2.52 volts, and now we're all the way at 15.916. So if we keep going up, I guess I could take it a little bit further to show you those spikes, but you see those spikes are going to keep getting larger and larger, even though our gain is diminishing. We do have those skew rate limitations being, you can see them right here in the oscilloscope, all the way up to, there's our 20 kilohertz, and you can see that definitely exists. to wrap this up, I want to go back down just to make sure that I can show you that. We'll go back to show you that it was decreasing the gain outside the band and increasing the gain or the magnitude, because the gain is supposed to be a unity filter. There's not supposed to be any actual gain that we're actually trying to create in it. It's supposed to just pass the signal in as it is, but it's just as attenuation. So as you can see, it's at 1.32 volts now. Now I'm going to drop it back now, and you're going to see that gain on the output yellow there slowly increase as I decrease the frequency. It's going to increase the gain. Increase the gain. We're at 15 now, and you see it's increasing, and then we're going to get all the way to we're getting right on 10. See how it's at 4 now? Look at that. See how once we crossed into 10, it went up, and how it's the highest part is around 5, 6, somewhere in there, and we're at 5 now. Okay, maybe it's at 3.68, 3.2. We're at 4, 3, 2, and once again you see the values go down again on the other side of the band at 1 and back down to 500 hertz. And there you go. Hope you enjoyed this demonstration.